All right, so as we move into this chapter, we're going to see a number that pops up that looks like this. And this is what's called an irrational number, because an irrational number is, for instance, a number that is as a decimal is really long and it has no pattern. It just keeps going. So it's something that's very difficult to remember. And what they do instead of using that number is they use a symbol instead, like pi. So this is an e, which represents this value, about 2.718, etc., etc. And this e, which is an irrational number, is known as Euler's number. And so what we're going to see in the coming days, that when things grow in the natural world, the rate of growth is related with this expression. So this guy named Euler came up with this. And what he did is he just figured this out, that if n, is your time, as time goes by, then what he noticed in this pattern was the number that appeared. So what I'm going to do to save time is I'm going to switch to the graphing calculator. I'm going to go here, and I'm going to type this in. And so I'm going to put in parentheses, 1 plus, I'm going to do parentheses for the fraction, so 1 over n, which I'll do x. I'm closing the parentheses for the fraction. There's the parentheses that you see, and I'm going to hit an exponent and put an x. So again, remember, this means as x gets bigger and bigger, so as time goes on and on, becomes bigger and bigger, what he realized, and let me jump to my table so we can start at 0, is that when he looked at a table, that this number, starting with 1, right, look at this value, it's growing. It's not growing very fast, but eventually, as the numbers get bigger and bigger and bigger, what happens, and I'm going to switch the table setting so I can type in any number I want, is that if I type in 1, I get 2. If I type in 2, I get 2.25. So we're just testing out different points of time. 10, I get 2.5937. And now we're going to make a pretty big jump in time, 1,000. And you get 2.7169. And now we're really going to jump and put in 1,000,000. So 1, and I put 1, 2, 3, 4, 5, 6 zeros. And what he realized is that bigger that number got, the closer this number stayed the same. And so since he realized this, he called this Euler's number. So first, let's just work a little bit with e. It's good for exponent rules. So remember, this means I have 3 e's and 2 e's, so that's a total of 5 e's. Anything to a 0 power, so again, it's just this number to a 0 power is 1. This would mean, this is your reminder from a previous chapter, that a 1/2 power is like the square root. Here you would subtract the exponents, so 5 minus 3 is 2, and my 2 e's would end up in the denominator because, okay, I don't know what that is, because there are more e's in the bottom. In this, I would multiply, so 2 times 1/3, which just gives me 2/3. So this would be e to the 2/3, which I could also write as a radical, the cubed root of e squared, all previous chapter stuff. And then anything to a negative exponent says it moves down, and once it moves, that negative exponent is gone. So just some rules with e. Remember, e is just a number. It can follow all the rules of everything else. So let's take a look at what happens when we graph with e. So again, anything to a 0 power is 1. E to the first power is about 2.7. I'm just going to stick with very simple decimals. And now I'm going to go to my calculator because I don't know. So real quick, e is on your calculator. There's this e, and then there's this e, which has a built-in exponent. So that's what I'm going to use. I'm going to hit second ln for that e to pop up. It shows the exponent. So I'm just going to put 2 in, and I get about 7.4-ish. And if I do the same and I just put in the third power, now I get about 20-ish, 20.1. And then the first power, again, that would just mean 1 divided by this 2.7 number, but I'll let the calculator do this for me. I get about 0.36, and then if I do this to the negative second power, again, it just means 1 over e squared, so 1 over 7.4, because that's e squared. I get about 0.14. So yeah, if you can see, I just typed all these into my calculator. And when we graph this, again, 0, you're going to get a value of 1. 1 is going to give me about 2.7. 2 will give me about 7.4. I can't get 3, but negative 1 is about 0.36. And what happens, the best way to do this also is to show you what if I just graphed this whole thing. And I want you to look at the table. And what happens, whoops, I don't want that version of the table, is when you look at the table, as e gets bigger and bigger and bigger, again, where did I mess up? Nope, I didn't mess up. Is that as e goes to a power, you know, you're going to see your numbers getting bigger. But the key is, as they get smaller, the y values, again, we talked about that when we saw e, it means 0. It just says that this number is 0, but it's not quite 0. So we have, again, that wall, which, let me graph this, that stands out. Remember, that wall is called a horizontal asymptote. And for now, it's always at y equals 0. I can't cross it. So I've got this shape that's kind of coasting along and looks like the others, which is similar to exponential, but it's unique because the base is e. So again, it will have a y-intercept of 1 and a horizontal asymptote of y equals 0. So it's the same as the other ones, but our base is consistently e. So if I did do this, remember, then I could just take this and put a 3, a negative exponent, a 4. So kind of going back to what we did in a previous chapter, remember this number in front would be like an a, right? Shoot. So as we do this, what we should see is this 3 is going to stretch it. So what will happen is this shape here is going to stretch. It's going to get skinnier. So if you graph 3 to e to the x, it says show the y-intercept in the horizontal asymptote. Excuse me. So again, 3 is where we begin. So that should be, okay, based on this, b times g to the x. b is our beginning, so I have a y-intercept of 0, 3. And what's going to happen, it's going to be very similar to this shape, right? Except it's going to be a little bit skinnier and it's going to stretch. So essentially what should be happening is, if we follow what we've done in other chapters, is these y values, which I'm only going to write a few of them, 0 and 1, 1 and 2.7, is that 3 would stretch it. So remember, we would multiply the old y values by 3 and get 3, and then 2.7 times 3, that's like 8 point something. Hold on. And you get about 8.1. So, you know, you're going to have this shape, I really need to switch colors here, that starts at 3, but it's just going to grow a little bit faster. Okay? This one, remember the negative exponent says it's just going to drop down and become e to the first power. And so what you'll see here is that this is actually just going to become decay. All right, like this. So our y-intercept is still 1, like there's a 1 hanging out here. 1 times, and it's going to be going down like this. And then this would be a stretch that is decay. So remember, how did I know it was this shape? When this number is bigger than 1, it grows. You learned this in Algebra 1. And when this number is in between 0 and 1, like that's a fraction, that's about 1/3, your shape goes like this. All right, and that's something that we already talked about in 7.1. So this is going to have a y-intercept of 0, 4, and it's going to be this decay shape. All right, so just some things we could put it in the graphing calculator just to experience what this looks like. All right, so what we're going to start to do is just work with this formula. We'll get into more details of these formulas later in this chapter. So let's see, this is our last example. So the population of a high school can be modeled by this. And so this is just more of a natural growth. That's what this is saying. And where P is the population and T is the time of year. So according to the model, when will the population reach 1,000? So I just put that over on the left side. And then we can go to Desmos. Let me just make sure that Desmos has E. So timeout. All right, so it does have E. You just have to type E from your keypad. All right, so I'm going to put in 1,000, one side. And again, to make it graph, I would need to put equals Y. And then I'm going to put 1,200. The E, just type in the e, and then I'm going to hit my exponent button. There we go. And I'm going to put in my exponent, negative 0.013 to the t or x power. So this is a negative exponent, which means that e would drop down into a denominator, and when 1 is over something, that number is always in between 0 and 1. So I should be seeing a decay shape. That's blue. I'm going to zoom in so you can see this way better. Okay, so we're looking to see, according to the model, when will the population reach 1,000? So right now, if you look at my time, holy moly, that's not very good. Let's go to the wheel and kind of mess with this. So if x is my time, let's say a high school, if the least amount of time I have is 0, then let's just go up to 50 years. X is time. And there we go. And then for y, if I'm thinking about the population of a school, you know, the least would be 0. And I'm going for 1,000. So I would like to go a little bit more than 1,000. So like 1,500. And then we should be able to see. And so again, there's that dot. So 14.012 is my time. So in 14.025 years, the population will have decreased. And again, the reason why I know it's decreasing is 2 reasons. One, it starts from here and it goes down here. The other reason is a negative exponent moves something down, and once it moves, it's down here. And when you take 1 and divide it by any number, that resulting number, okay, which we're calling g here, will be in between 0 and 1. And we discussed in our first section that when it's in between 0 and 1, it's decay. It's a shape that looks like this. So just a recap of that. Last question. According to the model, what will the population of the school be in 5 years? So I actually just have to go here and put 5 in. And again, since this is already in Desmos, I can just switch back. Let's find that page. I don't need the 1,000, and I'm just going to turn the x into a 5. So let's see, there's times 5. There's Ms. Simcox. So I'm going to put in parentheses up here. And there we go. So in 5 years, that population will be 1,124. We're just going to round to the nearest whole person. And that is the second part of 7.2. So sorry if you watched this video. I didn't do the notes ahead of time, so got a little flustered there, I will admit on that one. That's it. Take care.